Hello everyone. Today we're going to start talking about 3.2. So in 3.2 is actually a very important section because it laid the foundation on how we're going to represent solution set of a differential equation. Because of that, it's very important that you make sure you pay attention. It's also very difficult to understand because the concept is quite abstract. Okay, so to start, last year we learned to define vectors as lists, ordered lists of numbers. So last year we define algebraically vectors as ordered lists of numbers. So basically referred to as vectors in Rn. So what we're going to try to do this year is to kind of expand this concept of vectors to other objects that you might not think are vectors. The problem is that when we think of vectors, mostly we think about vectors in Rn, but there are other things that we can actually kind of define them the same way as vectors and therefore allow us to use what we know about vectors to kind of do math with it. So in this section, what we're going to try to do is the following. In this section, we will basically expand the definition of vectors into other objects. Now, but of course, the problem is that if we define other objects to be vectors, that's not hard to do. What's hard to do is to try to make sure that even if we define other objects as vectors, whatever we know about vectors still hold true. Remember, math is an internally consistent system. So when we do more definition, we have to make sure that whatever we define still work with existing definition and theorem. Otherwise, we'll create a system that's not consistent and therefore kind of make it fall apart. So, important thing about this is the following. When we define other objects as vectors, we want to make sure this is true. So these objects must have at least two basic operations that we know so that we can actually do math with it. And so what are these two basic operations? The same exact basic operation that you have learned back in chapter 1 last year, pretty much like the second day of school when last year. And those two things are vector addition. But of course, in here, when I say vector addition, that vector doesn't necessarily mean, when I say vector addition, when I say vector, it doesn't necessarily mean vectors in Rn, but could be any other object, as long as we can define it similar to what vectors would be. Vector addition, and you can probably recall the second operation that we did, and scalar multiplication. Okay, and we also want the following. We also want these objects along with the two basic operations must satisfy some properties. And the reason is because we want, when we define these objects as vectors, we don't want to force us to relearn some of this math or change some of the way we do things. We want it to be in such a way that it's kind of the same thing as we have learned already with vectors in Rn, but just expand to other objects and stuff. Now we expand to other objects, but now we restrict what we're allowed to do. So we don't want that. We want it to be similar to what we have already learned because we want to use what we already established about vectors in Rn to expand to these unusual objects that we don't think of them as vectors. Okay, but not the other way around. Not to restrict our operation or property that we already established. That's not what we want. So these objects, along with the two basic operators, must satisfy some properties. And when that happens, we'll be able to actually use them like they are vectors. And of course, one of the most important things that we eventually want to be able to do is the following. So remember, we talk about first day, I told you that we're learning linear algebra. And the reason is because we need to understand some of these stuff before we can talk about solution to a differential equation. And the idea is that differential equation, the solution actually follows some of the property about some of the concept in linear algebra. The problem is that the solution to a differential equation is usually a function. But linear algebra, as of now, based on what you have learned, is only relating to vectors in Rn. So that's where we have to kind of bridge the two things together. We have to learn enough to understand that how to actually talk about functions as vectors in linear algebra. And then I can use the concept of linear algebra along with function to actually talk about differential equation and the solution of it. Okay, so that's what we should try to do. So next we're going to try to do is to define something very important, which is basically the title of section 3.2, something called vector space. So what is a vector space? So let's talk about this. So given a set of objects, it really doesn't matter what this set of objects is. And we're going to call this set of object V. And it's a capital V with, let's say, two basic operations. And we really don't care how do we define these two basic operations. But these two basic operations should be similar to vector addition and scalar multiplication. And so here's the important part on what does it mean by a vector space is the following. Then V along with the two basic operations, these two basic operations, is called a vector space if it's satisfy the following properties. So what is this thing called vector space? The idea is to kind of try to use this set of objects to define a space similar to a space that we have been learning since last year. R2, R3, R4, like dimensional space, physical space. But these space, even though they are not physical, but we can imagine that they are. And that's what vector space is. Now, it might seem like it's hard to understand, but once we get through some example of them, then you hopefully will understand better. So what are this list of properties that must satisfy? So let's start with some of these. And some of these have names that you can write them down for yourself. First, if, let's say I have two vectors, vector u and vector v, and they are both within v. Then what must be true is that if I add these two things together, the sum must be in v. And if you want to write it down for yourself, that's closure property for vector addition. Number two, if S is a scalar and vector u is in v, then what we know is S times vector u is also in v. So this is called a closure for scalar multiplication. So we want to make sure that if I have two things within this set of objects, when I combine them together, the result will have to be still within this set of objects. It won't fall out of it. And closure, if you recall from last year, is very important because if an operation doesn't have closure, it will disallow us to repeatedly apply the same concept same operation over and over again, and pretty much screw up the math. So we want to have closure property. So both of these are basically called closure. Number 3. When you do vector addition, when you add u and v together, it always come out to be the same thing as v and u add together. So that's commutative property. Number 4. If you want to add 3 things together, and remember, because of the closure property, we're allowed to add 3 things together. You can say I can add the first 2 together, then add the last one. Or you can add the last 2 together, and then add the first one. And of course, combine that with property number 3, you can actually rearrange them and then add them together. Number 5. Now, this one is very important. Number 5. There is a vector, a very special vector in V, which we call this vector the 0 vector, such that this is true, such that when I take any vector u and I add the 0 vector to it, that is the same thing as taking the 0 vector plus the vector u, and it always can be vector u for all vector u in V. So in a sense, property number 5 is called the additive identity property. We have to have an identity element that allow me to add anything to it and it stays the same. And in this case, you can think of the 0 vector as the number 0 in our number system. Okay? And a few more. Number 6. Number 6. If vector u is in V, then there exists a vector negative vector u, meaning negative 1 times u in V, such that this is true. Such that vector u plus negative vector u give you the 0 vector. So that's called additive inverse, and meaning that if you have an object within this set, you must have an opposite object of that object within the set also. So you can undo each other. Okay? 7. Let S and T be 2 scalars, and maybe I'll do n vector u in V. Then if I take S times T times vector u, is the same thing as S times T times vector u. So that's associative property for scalar multiplication. Number 8. I know that's a long list of properties. Bear with me. Number 8. If you have vector u and vector v, both are in the set V, and S is a scalar, then S times u vector u plus vector v is the same as S times vector u plus S times vector v. And this is called a distributive property over scalar multiplication. Number 9 is similar, but it talks about if you have a scalar addition while you multiplying, what happen. So let's say vector u is in V, and we have S and T are scalars. Then S plus T times vector u is the same thing as S times vector u plus T times vector u. So it's also distributive property. And now is the last properties that we need to have, and that will be 10. Which states the following: if vector u is in V, then 1 times vector u would just be vector u. So these are 10 properties, but if you think about these 10 properties here, none of them are surprising. None of these are things that you don't know. As a matter of fact, our basic real number will satisfy all 10 of these properties. As a matter of fact, the set of real numbers are actually what we can refer to as a vector space. And in this scenario right here, if we do consider real numbers a vector space, then we actually call a single real number as a vector. However, we're not going to usually do that because we want to form a distinction between one single number being a scalar versus a set of numbers being vectors. Now, important to realize the following. Based on what we just talked about, a vector space must consist of the following things. Students often don't realize and keep on thinking that a vector space are just a set of objects, because that's what we use to describe the vector space. Okay? And you see that why once we talk about some of the example of them. But the important part is to realize that a vector space is not just a set of objects, but instead a vector space consists of the following. So make sure you pay attention to this. Note, a vector space consists of the following three parts. Number one, a set of objects. And this set of objects can be anything as long as it's fit into, we can define the next two things that we can do. And this set of objects are generically called vectors. And importantly is there is at least one unique object in the set. And that's called a zero vector. Okay, you cannot have a vector space without a zero vectors. Number two, two very basic operations. Two very basic operations. What are these two basic operations? Vector addition, which allow us to add two objects together, and scalar multiple, which allow us to multiply an object. Scalar multiplication. Allow us to multiply an object by a scalar. Important to realize you do not need to know how to multiply two vectors together. As a matter of fact, we will highly unlikely do anything like that in a vector space. Okay, and the main reason is because when you do a multiplication between two vectors, you're creating something that's usually not the same object, and therefore that's the reason why it doesn't work. So the two basic operations are vector addition and scalar multiplication of vectors. And number three, which is probably the most important of these, is that it must satisfy the set of properties. These 10 properties you must satisfy these 10 properties in order for you to define what is a vector space. Now, some of you might be confused as to, so what is this vector space? So, as I say, the idea here is to try to simply understand that a vector space, as the name suggests, is a space, meaning that it's like the XY plane that we have been dealing with is like the XYZ space that we're dealing with. The only difference is that when we deal with the XY plane or the XYZ space, we're using position vector to define position in space. But now we are using vectors, not define position in space, but define different object within this space that we created. But in a sense, we can actually visualize space with different objects, just like we could with XY plane and with XYZ space, because from a mathematical standpoint, we are doing nothing more than dealing with a list of numbers. So show you some example of that illustrate this concept. So the first thing I want to show you is this. So here are some examples of vector space. And we're going to start with the first one, which is the most basic one, and which we already know is a vector space, and it is the vector space that we have been working with since last year, chapter 1 in multivariable calculus. That would be vectors in Rn. To properly define a vector space correctly, I must define the following. Number one, what is the vectors in the vector space? So in this case, our vector, meaning the object that we define, would be vector x equal to x1, x2, to xn. So that is basically our object. Okay? 2, I must define two basic operations that allow us to actually work with this group of objects. Remember, a vector space has to be a set of vectors, basic operations, and set of properties. So the next thing I want to talk to you about would be the two operations. So we'll define the two operations the following way. If I have vector x plus vector y, then how do I add these two vectors together? It would be x1, x2, to xn, plus y1, y2, to yn, and therefore the sum would be defined to be x1 plus y1, x2 plus y2, to xn plus yn. So that defines our basic vector addition, which is the same exact way we defined it last year. And then we'll also go define our basic scalar multiplication, r times vector x. That will mean r times x1, x2, to xn, and that is equal to r x1, r x2, to r xn. Okay? And if you remember correctly, I told you that it's very important to make sure that your vector space has a clearly defined zero element. So in here, what would be our zero? What is our zero element? In this case, the zero element will be a zero vector, which would just be 0, 0, 0. And so now to claim that this set of objects, which is vectors in Rn, along with the two basic operations that we have, and with the zero element, it satisfies all 10 properties. So in this case, what we're going to need to do is kind of prove all 10 properties that are true. And of course, some of these properties we already know are true because from last year you already learned about them. But we can definitely try to write out some of these, and I'm not going to prove all 10 of them, but I would strongly encourage that you try to write out the proof for all 10 of them, or at least go for each one and understand and can argue why they're all true. So if you look at the list of 10 properties right here, the first two automatically satisfy the closure property, because if you look at just the way we define the two operations, the end result right here is definitely a vector in Rn, and this end result right here is definitely a vector in Rn also. So closure properties automatically satisfy. So maybe I just simply prove one of the properties right here. So I'm going to say, let's just prove let's say we just do the next property, property 3, whatever 3 is, property 3. Number 3. And as I say, you should definitely try to write out the proof for all the properties to make sure that you understand. But if you don't, simply because you already learned how to do that last year, then it's probably okay. But you should definitely check, fling your way through each one of them at the very least, just to make sure you understand that they all satisfy and they're all okay, even if you don't write out the proof. So I'm going to write out a proof for property number 3. So we're going to start with the following. So what we basically try to prove is this. We're trying to prove that if u and v are in our set of v, vector u plus vector v is the same as vector v plus vector u. So let's start with the following. So in our case, set v right here is basically vectors in Rn. And I have to define two vectors that is in Rn first. So it shouldn't, we can just simply define them like we normally would do. I'm going to say, let's say we have vector u and vector 3 within Rn. So therefore, tell me that vector u is u1, u2, to un, and vector v is v1, v2, to vn. So now what I'm going to do is I'm going to try to add these two vectors together and see what happens. So therefore, it's just u1, u2, dot, 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 plus un, plus v1, v2, dot, 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 vn. And now remember, just like what you probably remember doing last year, what we're going to try to do now is to use property of real numbers to help us prove this is true. And to do that, I'm going to try to just simply do my vector addition and see what happens. So vector addition, the way we define vector addition, tell me that I simply add the corresponding number together. So u1 plus v1 become the first element. Oops. u2 plus v2 become the second element, and then dot 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 to un plus vn. And now, since addition between two real numbers are commutative, I can now then say, well, that would technically be the same as v1 plus u1, v2 plus u2, dot dot dot, plus vn plus un. And now if I think about it, let's say this is my left-hand side, then our right-hand side would just be vector v plus vector u, which would just be v1, v2, dot, 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 vn, plus u1, u2, dot, 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 to un. If I do combine them together, that just becomes v1 plus u1, v2 plus u2, dot, 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 vn plus un. And guess what? That looks surprisingly the same as what we had on the left-hand side after we manipulate a little bit. And so now, therefore, I can now conclude that vector, Now that I see this, I can now conclude that vector u plus vector v is the same as v1 plus u1, v2 plus u2, dot, 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 to vn plus un, and that just so happens is the same as vector v plus vector u. And so that completes my proof. Property number 3. And you can simply write out some of these other properties, and yes, you will be asked on your test to prove vector spaces or be asked to prove some of the properties of a vector space. So be aware of that and make sure you know. And if you don't remember, you should look back in your notes to see what the expectation would be, because I'm going to expect the same exact thing like last year in chapter 1 when you first learn about writing proof like this. Okay, and if you don't remember, I would still strongly suggest you go back to your notes and take a look, and if you really can't find it, you can definitely ask me during class, and then we can go over the requirement or the expectation. So now this is not that exciting because I mean, we already kind of know that would work. So how about talk about some different stuff? Some other things that you don't think of them as vector. As a matter of fact, we haven't presented them as vectors, but we can actually look at them as vectors. Okay? And number 2. So number 2 is often referred to as matrices, matrix space. Okay? So what does it mean by a matrix space? So let's start with the following. We're going to define this. Let's say for 2 scalar, let's say m and n, we can define, let's rewrite this. We can define the vector space as follows. The vector space m, n as a subscript to be the following. So remember, to properly define a vector space, I have to first define what are the set of objects that we're creating. So the set of objects would be the following: the set of all m by n matrices. So that would be a set of objects. But remember, with a set of objects being with a set of objects, I still need to define basic operations and also show that they satisfy all the properties. So here would be my basic operations. So the two basic operations would be just the same way that we define matrix addition. Oops. So matrix addition, which basically would do the following. If I take two matrices, let's say matrix A plus matrix B, then that would just simply be what A11 dot 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 to A, oops. Okay, there you go. A and M, AM, I'm sorry, A1M. There you go. A1N, I'm sorry, A1N. And then dot 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 to AM1, dot 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 to AMN. Plus B11, dot 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 to B1N, dot 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 to BM1, dot 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 to BMN. And that sum would just equal to A11 plus B11 dot 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 to A1N plus B1N, and then dot 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 to AM1 plus BM1 dot 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 to AMN plus BMN. So that's our matrix addition, which basically just add the corresponding entries between the two matrices together and to form a new matrix. And then how about scalar multiplication? So if I have R times matrix A, that just being R times A11, oops, A11, dot 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 to A1N, dot 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 to AM1, dot 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 to AMN. Okay, and that just equal to RA11 dot 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 to RA1N dot 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 to RAM1 dot 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 to RAMN. So that's how we're going to define these two basic operations: matrix addition and scalar multiplication. And some of you already kind of probably noticed the similar trend here. And I already know how we're going to prove that this is indeed a vector space. But before I continue, I do need to also define the zero. So the zero would be the zero matrix. I'm going to say capital O will be the zero matrix. And what is the zero matrix? Capital O would just equal to 0 dot 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 0 dot 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 0 dot 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 0. It would be just a matrix with zeros in it. Now, and what I'm claiming is that this will form a vector space. And I already defined the object, I already defined the operation, I already also identified what is the zero element within my matrix. So how do I show that this is a vector space? Well, I could go through the same process as Rn and simply just prove all 10 properties. And that can be done. And as a matter of fact, if you want to try that, you should give it a try. But hopefully that after you prove a few of them, you realize what you try to do and understand that you can simply just use this argument right here. So how do I know that this is a vector space? So to see that Mn is a vector space, we can simply think of this as the vector space Mn as the vector space R to Mn. So example, meaning the following, meaning that if you look at the vector space M, let's say 3, 2. So that, technically speaking, is basically a matrix space of all matrices that have 3 rows, 2 columns. Okay? But if you think about realistically, if you have a matrix space, a matrix that have 3 rows, 2 columns, then how many entries are inside? There are 6. There are 6 numbers inside. And what's stopping you from listing them just one single row and make it into R6? Meaning, let's say if I have a matrix, let's say 1, 2, 3, 4, 5, 6. So that would be a matrix in M32. Well, guess what? That matrix is the equivalent to a vector 1, 2, 3, 4, 5, 6 in R6. And therefore, if this would form a vector space, any vectors in this form form a vector space, then any matrices in this form would also form a vector space because they are mathematically identical. Okay? So that's very interesting. So therefore, meaning that now we can actually look at a set of matrices as vectors and do things that we know about vectors to them. And this is probably the most important concept that you need to understand. And I think my video is getting a little too long. So this is the last thing I'm going to talk to you. And then we will continue to show you more example vector space in tomorrow's video. So, but this is probably the important concept. What we try to do with vector spaces. What is the end goal here? What do we try to accomplish by talking about vector spaces? Is the following. Is to try to take objects that we don't usually think of as vector space, as vectors, but somehow turn them into a vectors like we know from since last year. So the idea is that a lot of these problems that we're going to be doing, a lot of these vector space that we're going to be defining, we'll kind of eventually just turn them all into Rn. And then we just use what we know from Rn to do math with it. That's basically what we're going to try to do eventually. Just like here, we have a matrix. But instead of looking at it as a matrix, we actually turn it into a vector. Like instead of looking at a matrix of 3 by 2 matrix, I actually look at it as a vectors in R6. So now all of a sudden, everything that you learned last year about vectors in R6 or in general Rn will now automatically now apply. And you can now do a whole bunch of things that you normally wouldn't do with matrices. Now you'll be able to do them because you don't look at them as matrices. You're looking at them as vectors in Rn. All right. I think we'll stop right here for today. And I'll show you a few more examples of vector spaces tomorrow. Okay. Talk to you guys tomorrow. Bye.